The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everybody. Welcome to the webinar. Today we are here with Matt Piantedosi from the Cadmus Group, and we're going to talk about electric power monitoring with the HOBO data loggers. Just real quickly, Onset Computer, kind of who we are. We're the world leader in data loggers. We were founded in 1981, so we're actually going into our 31st year. We have about 120 employees. We do all of the manufacturing, design work, everything here in Bourne, Massachusetts on Cape Cod. We've sold over 200 million HOBO data loggers to date. And a little bit about Matt Piantedosi. He's an associate engineer, master electrician for the Cadmus Group. Has over 11 years experience in the electrical field and over 4 years in energy efficiency. He's installed over thousands of data loggers ranging from residential lighting to industrial power, and leads the field measurement team and oversees safety operations at Cadmus. And I am going to turn this over to him so we can go from here. Welcome, Matt.
Thank you, Scott. Okay, so today a little brief agenda. We'll talk about the HOBO data loggers that we'll be using. We'll go over important electrical safety considerations, and then we'll jump right into energized power metering and the logger installation. So the equipment we'll be working with today, starting with the top left, is the U12 with a CTV. Then I'll show you how to install a U30 with a watt node in an electrical panel. And then finally, the UX120 with the E50 B2 power meter. We'll now discuss important electrical safety considerations. Today's presentation will provide an overview of installing power metering equipment in electrical panels. This presentation will not qualify you to perform such installations. It is critical that only qualified persons with the appropriate knowledge and safety training install these devices. Failure to do so will result in major injury, loss of life, and/or property damage. We recommend licensed electricians for this work. A few safety statistics. On an average of 30,000 electrical contact injuries annually in the U.S., electrocutions, deaths account for about 10% of construction-related deaths. Over 50% of these occurred on less than 600 volts, which is typically the panels that we usually work in. It's the fourth leading cause of industrial death, and only 7.5 watts at 120 volts is more than enough to kill you. If something were to happen, an arc blast, copper expands by 67,000 times its solid volume during an arc event. Sound can exceed 160 decibels, rupturing the eardrum. Shrapnel leaves the arc blast area at speeds exceeding 700 miles an hour, fast enough to completely penetrate the human body. Pressure wave can damage lungs, brain, and central nervous system. And here's the latest safety that will follow. If we go over to table 130.7 C15A in the 2012 edition of the NFPA 70E, Standards for Electrical Safety in the Workplace, this shows us that when working with panel boards greater than 240 volts and up to 600 volts, we must wear the safety equipment in compliance with Hazard Risk Category 2. Table 130.7 C16 shows the equipment associated with Hazard Risk Category 2. We will go over each piece in the following slides. So starting top to bottom, we have the face shield system. In addition, we have to wear safety glasses and hearing protection. We also have the balaclava. This is different from the firefighter equipment. This has to have an arc rating of at minimum 8 calories per square centimeter. We then wear the arc flash jacket. Again, the arc rating of 8 calories per square centimeter. Or we can wear a flame-resistant shirt, again with the same arc rating. We wear rubber insulating gloves. We want to make sure that they're class 00, and leather protector gloves, so during an arc blast, the rubber will not melt. This will also help the rubber from abrasion. And then we must wear flame-resistant pants or overpants, again with the same arc rating of 8 calorie per square centimeter, and then leather work boots. Many facilities that we visit will require steel toe shoes, and those are okay as well. And now we'll get into some safe work practices. And these are just a few examples of what we follow at Cadmus for all our employees. Never wear synthetic clothing, including undergarments. We want to make sure that we only wear 100% cotton clothing or the flame retardant clothing that we just discussed. Never wear open-toed shoes, jewelry, or loose clothing, and we always wear our safety glasses no matter what. Before we open an electrical closure, it's important that we know how to shut down the equipment in the event of an emergency. We always want to resist hurry-up pressure. We never try to attempt something that we're not comfortable with. We only use electrically insulated tools inside the electrical equipment. And whenever possible, we want to de-energize the equipment before making our installation or removing data loggers. Again, I say whenever possible because sometimes we'll need to do an energized voltage test. We'll want to use a voltage tester to verify the presence of voltage. I'll discuss voltage testing a little bit later on. And we'll also want to remain in visual and audible contact with workers performing the work. So it's good to work in pairs or in small groups whenever possible. And now we'll get into energized power metering. Before we install metering equipment in an enclosure, it's always best practice to identify and confirm the voltage we're working with. This will not only help determine what equipment is required, but also ensure the appropriate PPE is worn. The first test should be a basic visual to identify any labeling or color coding. If the enclosure isn't marked with the voltage, we should always assume it is higher, 480 volts in most cases. Once we are wearing the proper PPE, it is safe to remove the cover to gain access to the conductors. Here we can see if there is any color coding to help confirm our voltage assumptions. Typically, black, red, and blue are used to identify 120 208 volt systems, and brown, orange, and yellow are used to identify 277 480 volt systems. Here are examples of each voltage configuration. On the left we have a 208 volt panel board, and on the right we have a 480 volt panel board. Once we have a solid idea of the voltage, we should verify it with a voltage meter. It is important that the meter we use is double insulated and has at least a Category 3 rating. We will now watch a short video on how to perform a proper voltage test. We'll now perform a voltage measurement on this energized panel board. We'll do so by wearing all of the necessary safety gear that we previously described. It's important that only qualified persons enter the panel board. Start with our safety glasses and hearing protection. And now our balaclava. And now I'll put on my 8 calorie arc flash jacket. And I'm wearing my 12 calorie arc flash pants. And I'll put my first layer of gloves on. These are to absorb the moisture. These are followed by my Class 00 500 volt voltage insulators and my leather protectors. and I'm now ready to remove the cover of the energized panel board. We can see that the main conductors are black, red, and blue, so we know this panel is probably 208 volts. We'll confirm that with our voltage meter. We'll take our voltage readings with a Fluke T5 1000 meter. This is double insulated and good for up to 1000 volts. We'll set the meter to voltage, and we'll take multiple voltage measurements. We'll start with phase A to the neutral conductor. We should read approximately 120 volts. We'll then move on to phase B and phase C and get the same reading. We'll then check the voltage phase to phase, measure the voltage between phase A and phase B and phase C, and phase A and phase C. For this, we should read approximately 208 volts. Once we've confirmed our voltage, we can now install our data logging equipment in the panel. Okay, so as you can see, that panel actually was not live, but I just wanted to demonstrate what it would be like wearing all of the equipment. Now that we've identified the voltage we're working with, we will be metering. We must determine a safe location for our equipment. The location must be large enough to accommodate the equipment, free from sharp edges and moving parts, and easily accessible for both safe installation and removal. An ideal location is one that has minimal impact on the safe operation and maintenance of the equipment. The best location for a watt node is typically at the bottom interior of the electrical panel, as we can see here in this photo. The next couple slides will give us examples on where to place voltage leads. Here are voltage leads on fuses in electrical switchgear. Here are voltage leads and CTs on a circuit breaker in a motor control center. This photo shows the watt node placed at the bottom of the enclosure and CTs on the lower left circuit breaker. The voltage leads are not yet connected to the power source. Here is an example of a completed installation before the cables are organized. We can see the watt node at the bottom of the enclosure, voltage leads on the appropriate phase conductors, and CTs right under each voltage lead. We will now discuss the installation of a simple current meter. Current metering is the most basic type of measurement. It is best for runtime and can be used as a rough estimate of energy consumption. For this, we'll use a U12 data logger with a CTV-A. It is always best to locate the CTV inside the enclosure and the data logger on the outside. This will ensure safe launching and reading out of the logger. We will now watch a short video of an installation. We'll now install a data logger on a single circuit to monitor the amperage. We'll do so by using an on-set HOBO U12 data logger and a CTVA, which is a split-core current transformer. This particular current transformer is not directional, so it doesn't matter which end the wire goes in. We'll be working with our demonstration panel board, which is de-energized, so we can focus on the meter installation. If this were an energized panel board, I'd be wearing all the necessary safety gear to work in it. Once we've identified the circuit to monitor, we'll install the CTV around the conductor and line up the conductor in the center of the CTV and clip it closed. And now we'll need to run the data cable on the outside of the enclosure. We'll do so running it through this fitting. That way it'll provide a safe method of exiting the enclosure. And we will now connect the data cable to our U12 data logger. And we'll mount the data logger with one of the many methods provided with the packaging, in this case a magnetic strip. and we are now ready to launch our data logger. Okay, next on the agenda is monitoring the power of a single circuit. Power or energy metering is a bit more complex than current metering, but it is much more accurate when we need to know energy consumption over a period of time. It can also help us determine peak usage of a specific piece of equipment, circuit, or an entire distribution center. For this next installation, we will monitor a 50 amp 3-phase circuit with a watt node and a U30. After we verify the voltage, like in the previous example, we can determine the proper watt node for this installation. A watt node or voltage leads should never be installed on the outside of an enclosure because it is normally connected to hazardous voltages. It is also very important the watt node model matches the voltage you are working with. For this installation, we will be using a T-WNB-3D-240-P watt node. The product application specialists at Onset can assist with the proper watt node selection, as there are many different models. We will now watch a short video on the watt node installation. We will now monitor the energy on a single circuit using a watt node and a HOBO U30. Once again, we'll be doing this on our display panel board, which is de-energized, so we can focus on the equipment installation. If this was a live panel board, I'd be wearing the necessary safety gear. We'll start out by identifying a safe location for our watt node. For this installation, we'll use the bottom of this panel board right here. We'll locate our CTs on these conductors for this 50 amp circuit, and our voltage leads can either go up here or down here, or if available, they can go on these conductors. These panel boards are wired phase A, B, and C, left to right, and top to bottom. We'll start by wiring our CTs to the watt node. We'll use a split core current transformer. Again, these are directional. I've also labeled the CTs black, red, and blue to represent the phase colors. These line up with the colors on the watt node as well as the colors in the electrical panel. We start out by wiring the black CT to the phase A terminal to the white and black terminals. We'll then wire the red CT to our phase B terminal. Once again, the white wire will go on the white terminal and black wire will go on the black terminal. And lastly, our phase C CT, the blue, will get wired to the phase C of the watt node. We're now ready to plug our voltage leads into the watt node. For this, we'll use the watt node lead set available from Onset. This particular lead set is double insulated and rated for 1,000 volts. Now that our watt node is pre-wired, it's ready to install. We'll place the watt node in the location where we've determined. We can now run the Onset pulse input adapter cable to our watt node. We'll do so using the listed fitting to bring our cable into the panel board. And we'll wire it directly to the watt node. This cable has a black and white conductor the black will be connected to the common, and the white wire will be connected to P1. Normally we will not use P2 and P3. Now that everything is wired to the watt node, we can begin connecting our CTs to the phase conductors. We will start with the black phase A CT. This will go around the black conductor on our circuit. Once again, this particular CT is directional, so we want to make sure the arrow faces the source, or in this case, faces the center of the panel board. And this CT just clips shut to know we have a secure connection. We'll now move on to the red, phase B. Make sure the arrow faces the source, and this will go around the red conductor of our circuit. And lastly, our blue CT, phase C, will go around the blue conductor. And we'll want to tuck the CTs in deep enough to allow for the enclosure cover to be installed. We'll neaten our CT wires, and then we can move on to our voltage leads. We'll start with the green ground voltage lead. This can be connected to any part of the metal in the enclosure or one of the two ground bus bars in this panel. For this, we'll connect it up in this corner. We'll want to make sure it's nice and secure, and we'll run the cable safely along out of the way of the other cables. The next connection will be the white neutral voltage lead. In this particular panel, the neutral bus bar is on this side and this side, and for convenience we'll go right over here. Again, we'll make sure we have a good secure connection, and we'll neaten up our lead. Our next connection will be our phase conductors. These are the most dangerous connections we'll be making. For this, we'll connect our black phase A right over here. And once again, it's very important that the connection is solid and also not touching any other metal. We'll do the same with the red phase B conductor. We'll test our connection, make sure it's solid, and ensure that it's not touching any other phases. And finally, our blue phase C conductor will go to this bus bar right here, which is connected to phase C. Once we have our voltage leads in place, we can use a zip tie to organize them. And we'll tuck them out of the way of the enclosure cover. We'll want to see the indicator lights on the watt node once we repower the circuit. We can now plug in our onset pulse input adapter cable to our HOBO U30 into any smart sensor port available. And now we're ready to launch our data logger. Okay, and once all the connections are made, the watt node indicator lights will illuminate and may begin flashing. To ensure the watt node is connected properly, we observe the indicator lights with all the equipment running. If all three lights are flashing green, we're in good shape. If the lights are flashing red or yellow, we must refer to the watt node installation manual for proper troubleshooting. If the equipment is not running, it is normal to see the green lights on or lights flashing very slowly, green, yellow, or red. Before we go any further, we had a question regarding making up the connections with the gloves and the installation with all three pairs of gloves on. Now, one thing that we do at Cadmus is, if you saw earlier on the video, outside of the electrical panel I made all the connections onto the watt node. We can do that without the gloves on, so then all we have to do is wear the gloves inside the electrical panel. The final topic we will cover today is monitoring whole electrical panel. We will do so with an E50B2 power meter and a UX120 data logger. The E50B2 meter is the most accurate way to monitor many electrical conditions simultaneously, such as voltage, current, power, power factor, energy, and many more. This particular method is more for a permanent installation and is therefore recommended that only a licensed electrician perform this. Like the rest of the installations we discussed today, the best teams are made up of an engineer that understands the logging equipment and a qualified person to work inside the enclosures. Once we determine the enclosure to monitor, we will look at the desired location for our equipment and come up with an installation plan. Because this is a permanent installation, we will want to de-energize the equipment. It may be necessary to schedule this process with a facility manager to ensure all parties are aware of the interruption of power. Once this is done and we are ready to move forward, we will shut down the equipment and follow the lockout-tagout process as described in the 2012 edition of NFPA 70E. The following video will go through the installation process. We'll now install a data logger to monitor the whole panel power. We'll do so by using an onset E50B2 power meter and an onset HOBO UX120. Since this will be a permanent installation, we want to make sure that we safely de-energize our panel board that we're working in. We follow the lockout-tagout process as described in NFPA 70E. For the E50B2, we'll install a standard 10-inch by 10-inch by 4-inch metal enclosure. We'll run a 1-inch conduit between the enclosure and the panel board for our 5 voltage leads in 6 CT conductors. For our UX120, we'll install a plastic enclosure with a plastic 3/4-inch conduit for our 6 communication conductors. For this installation, we'll use the Velcro mounting method in order to have ample space for our data connection. The E50B2 power meter will mount directly to the 39mm DIN rail. When we install the DIN rail, it's important that we leave enough room above and below for the wiring to the meter. To install the meter, we connect to the top half and then push down on the bottom half until we hear the click. Now that the E50B2 power meter is in place, we can remove the terminal covers and begin to wire it to the UX120. For this, we'll use the E50B2 lead set available from Onset. We'll run the black and white conductors up to the UX120. We'll start with channel 1 on the UX120. And we'll connect the channel 1 lead to the volt-amp reactive hour terminal on the E50B2. We'll now connect our next conductor to channel 2 of the UX120 logger. This cable will connect to the watt-hour terminal on the E50B2. We will now connect our final lead to channel 3 of the UX120. And channel 3 will connect to the amp hour terminal of the E50B2. We can now organize our conductors with a cable tie. We can now install our 3 CTs on the main feed of our panel. Once again, these CTs are color-coded, black, red, and blue, with our 3 phase conductors. We'll start with the phase A CT on the phase A conductor. These CTs are directional, and it's important that the arrow faces the source, or in this case, faces up. And these CTs just clip closed. And we run our CT conductor back through the 1-inch conduit to our E50B2 meter to the phase A CT terminal. Because these CTs are directional, it's important that the white conductor connects to the positive terminal and the black conductor connects to the negative terminal. We'll now connect the red phase B CT to phase B of our panel. Once again, we make sure the arrow faces the source, and we clip the CT closed. We pull the CT conductor through the conduit and connect this to the phase B CT terminal on the E50B2. The black conductor connects to the negative terminal, and the white conductor connects to the positive terminal. Our final CT is the blue phase C CT. Once again, we line up the arrow with the source, connect the CT around the conductor, and clip it closed. We'll run our final CT conductor through the conduit to the phase C terminal of the E50B2. The black conductor once again will be connected to the negative terminal, and the white conductor will be connected to the positive terminal. Now that all of our CTs are installed, we can organize them with zip ties. And we'll pull the excess wiring into the enclosure. And once again, we'll organize these conductors with a zip tie as well. We can now put our terminal covers back on the top terminals of our E50B2. We'll now install our voltage lead set on our power meter. We'll connect the phase conductors to the lower left-hand side, and we'll also connect conductors to the lower right-hand side to power the meter. We'll start with our green ground connection. This connects to the left-hand terminal of our control power block. Our next connection is our white neutral conductor. This will connect to the far right terminal of our voltage input terminal block. We will now connect our black phase A terminal conductor to the far left phase A terminal as well as terminal number 1 in our control power terminal block. So we bring the black phase A conductor together with the terminal 1 conductor on the control power using a listed terminal. We'll now make the same connection for the red phase B conductor, connecting that to terminal 2 on the control power. And we bring the red phase B conductor together with terminal 2 on the control power using a listed terminal. We'll now install the blue phase C conductor to phase C on the voltage input terminal block. Now that all of our phase conductors are installed, we can install our terminal block covers. We're now ready to bring our conductors into the panel board. We will now connect the green ground wire to anywhere on the ground bus bar, which is right up here. We'll now connect our white neutral conductor to the neutral bus bar. And now we'll connect our 3 voltage leads to a circuit breaker. For the safest installation, it's recommended that we use a 15 amp circuit breaker and we connect it right into the bus bar. It's also important that the breaker phases line up with the panel. In this panel, we have phase A at the top of the breaker, followed by phase B and phase C. We'll connect the black conductor to phase A. The red conductor to phase B. And the blue conductor to phase C. Since this is a permanent installation, we can now organize our conductors. Once all the wiring is in place, we can double check everything and turn our panel board back on. Once this is done, we can turn on our new circuit breaker, and we should see a display on the E50B2. And now we're ready to launch our HOBO UX120. Okay, at this time we should all be experts on how to install this equipment. We got a number of great questions which I'll begin to answer. The first question came in regarding the listed fitting that I used to bring the pulse input adapter cable into the panel board. The question was regarding what do we do after, because I mentioned that the watt node was a temporary installation. Is there a cap for this? This fitting that I used is a standard SJO cord fitting. The way this works is if you screw it completely tight, it'll actually close the hole. So you could use that same fitting to cap afterwards. Or what you could do is the fitting can also be removed, and you can use a standard knockout seal that can be installed in the enclosure. All of these holes are standard trade sizes. That particular one that I used was a standard 1/2 inch connector. The next question was, can voltage leads be clipped directly to the main lugs if there are no breaker positions available? And basically, as long as this is a temporary installation and the voltage leads remain inside the enclosure, this is okay. It is always best practice to install the voltage leads on a circuit breaker or fuses, but in some cases we don't have a choice, so we will go on to the main lugs. Once again, under no circumstances shall the voltage leads leave that enclosure, as they are live and very dangerous. One other question we got was regarding the presentation. This presentation will be available to download after the session. Another question came in during the last video. What is a listed terminal? As you can see, I brought some conductors together under the E50B2, and I mentioned a listed terminal. And this could be a number of things. This could be a wire nut, an insulated screw terminal, an insulated crimp terminal, basically anything listed to bring 3 conductors together. Another question came in regarding the sub-enclosure that I installed for the E50B2. They asked if the safety gear needed to be worn while working in that particular enclosure rather than the electrical panel board. Basically, I installed 2 enclosures for the reason that we can work on everything safely. So what we can do is the circuit breaker that controls the E50B2, we can turn that off. Now everything in that metal 10x10 enclosure is completely de-energized, and we don't need to wear the safety gear. Furthermore, even with that enclosure energized, we have the E50B2 in the plastic enclosure right above it, completely isolated from any hazardous voltage. So with the E50B2 running, we can safely download our data logger and not worry about any hazards. Another question came in regarding phase conductors, and CT leads. So as you saw, I ran a 1-inch metal conduit between my 10-inch by 10-inch enclosure and the main panel board, and I mixed the voltage leads in the CT conductors. For short runs, this is okay to do. For longer runs, I would probably recommend multiple conduits. And we'll go through a couple more questions. Do the connections between the logger and the meter have to be twisted pair? That's the black and white conductors between the E50B2 and the UX120. And to the best of my knowledge, they do not have to be twisted pair. The conductors that come into the in the lead set, the E50B2 lead set, are twisted pair, and they are black and white. One thing that I didn't mention in the video is that those conductors between the E50B2 and the UX120 are not polarized, so we don't need to worry about positive and negative connections. Another question came in. Okay, another question came in regarding industrial settings. Is there an easy way to tell the difference between 3-phase 3-wire and 3-phase 4-wire? Basically, the simple answer is 3-phase 4-wire will have a neutral connection. So if you look at during my watt node installation, I connected the neutral conductor, but if you notice to the 50 amp circuit breaker, it was just straight 3-phase. There's a good chance, depending on the equipment, that there actually was no neutral connection, so the watt node wouldn't need that neutral connection. I always say, to be safe, just connect the neutral if one is present. In some industrial enclosures, there will be no neutral bus bar, in which case the neutral wire isn't necessary for the watt node. And we'll just go through a couple more questions here. Oh, okay, here's one regarding the reading and the conductor inside the CT. Now, I mentioned that the most accurate reading will be if the conductor is perfectly centered in the CT. That's what the manufacturer's instructions say to do, but if it's not perfectly centered in the field, I haven't noticed a major difference in accuracy, so I think it's okay. We just try to make sure the conductor's closest to the center of the CT the best possible. And I'll turn this over to Scott. He'll address some of the other questions that came in.
Hello again. There was a couple questions here regarding the data loggers themselves, and I'll take some of those here. So one of them is what's the cost of the UX120 and the E50B2 setup? You're typically looking at about $950, right about there, when that includes the leads and the E50B2 and the CTs and all of that stuff there. Another question that we had is there a cost-effective way to monitor all the circuits in the panel? There's a couple different ways you can go about doing that. The first solution that Matt showed was with the U12s and just recording the amperage. So you can take that approach just by the 4-input CT, obviously, 4-input U12. You obviously have to use multiple of those. Another way to tackle that is one of the watt nodes, rather than monitoring all 3 phases, it actually has 3 pulse outputs, so with one watt node you can record 3 single phases. It really depends upon how accurate your measurements want to be. But what I would do is actually definitely contact our application specialists here at Onset, and they can step you through that. There are a couple other questions here, but we're kind of running short on time. So what we're going to do is save the questions for later, and we will respond after this webinar. As Matt previously stated, this will be available. We'll send an email follow-up, and I know the videos were a little bit choppy. on some computers, so they will be available on YouTube afterwards. So stay tuned, and thank you, Matt, and thank you for everybody for being here. And contact information, if you need to get in touch with Matt at the Cadmus Group, and also anybody here at Onset. And if you are outside of the U.S., we do have a number of dealers located throughout the world. So thank you again, and have a great day.